4.1 has to do with things called maxima and minima of graph. So when we're talking about 4.1, we're looking at different ways that we can figure out the largest y value attained, that's the absolute maxima, and the smallest y value attained, that's the absolute minima. So to find these, we can use some techniques from calculus to help figure out where these are. For example, if we look at graph A, this graph here has an absolute minima, and it happens at x equals 1, but the absolute minima is y equals 2. And so that's what the first part here says. Absolute minima, y equals 2 at x equals 1. There is no absolute maximum because these go off to infinity. It never stops. Here's an example of a graph that doesn't have absolute minima nor absolute maxima. Notice it goes off to infinity on the right, so it's positive infinity, and negative infinity on the left. So there isn't a biggest or smallest y value anywhere on that graph. So that's the maxima and minima stuff that we have here with these pictures. Now what the theorem says is if you have a function that's continuous on a closed interval from a to b, then f of x has an absolute maximum and minimum on that interval. And here's an example, y equals x squared. Y equals x squared will go up and down forever. So it would have an absolute minimum, but not necessarily an absolute maximum. But they give me a closed interval. They tell me that x goes from -2 to 1. So since the function is continuous, that means I don't lift my pencil off the paper when I draw the picture. So if I draw a picture and I don't lift my pencil off the paper, well then there's got to be a biggest place I drew and a smallest place I drew if there's a closed interval. In this case, the absolute minima happens at y equals 0. The absolute minima is y equals 0, and it happens at x equals 0. That's the smallest value possible. And that's something called a local minima. We'll talk about that in a second. The absolute maxima, that occurs up here where the biggest y value is. Now notice, if I hadn't closed the interval, the graph would have kept going, and so there wouldn't have been one of these. But since the interval was closed, I can find an absolute maxima. The absolute maxima is at y equals 4. That is the maxima, y equals 4. And it happens at x equals -2. So you can identify these from graphs by looking at the graph and seeing where the biggest y value and the smallest y value are. And by definition, if the interval is closed, you can always find a biggest and smallest value. Local max and minima, these aren't absolute. Absolute is the biggest y value, absolute maxima. Absolute minima is the smallest y value in the whole graph. But we can also talk about local maxima and minima. These are also called local extrema. And these have to do with places in regions that are the biggest or smallest y value. So here's some pictures that show you some local max and mins. Here's a local minima because in this region it's the smallest y value. Is it the smallest y value of the whole graph? No, because the ones over here go all the way to negative infinity. This area here is a local maxima because it's the largest y value in that region. Is it the largest y value on the whole graph? Well, no, those go all the way out to positive infinity. So notice local minimum are valleys and peaks. That's really what they become. And if you want to see how we define local minima, you can look at the tangent lines, which are these blue lines that are drawn on a graph. These blue lines are the slopes of the tangent lines. You can see these little tangent lines drawn in here. Negative slope, 0 slope, positive slope, 0 slope, negative slope. Notice the peaks and valleys occur where the slope of the tangent line is 0, because you get these horizontal tangent lines. Well, those are called critical points. They're where local maxima and minima are defined. They're where the first derivative, which is the slope of the tangent line, is 0 or undefined. So here's a picture that shows you what happens where the first derivative is 0. That just means the tangent line is horizontal. Happens at peaks and valleys. And the other one is where the first derivative is undefined. So the critical points we're about to talk about are the values of the independent variable, they're the x values, where local min or maximas occur, and the maximas are the y values. So we figure out where it happens, the x value, and then we plug that in to figure out what the y value is where that happens. And these critical points are the x values, and you find them by figuring out where the first derivative is 0 or undefined. And so we're just going to find local maxima and minima. These are the local max and min values. And we do this by finding critical points. So I'm going to find the critical points of this function by taking the derivative. The derivative of this thing is 6x minus 4. There are no places where 6x minus 4 is undefined, because it doesn't have any fractions in it. There's no square roots to mess us up. So it's defined everywhere. So the only critical points we're going to have are where this first derivative is equal to 0. And so I end up getting x is 4/6, which is 2/3. So there's my critical point. Two-thirds. To find the extreme value, I plug the 2/3 back into the function to figure out the y value there. In this case, I get f of 2/3, which is 3 times 2/3 squared minus 4 times 2/3 plus 2. And I get 2/3 out when I plug 2/3 in. So the extreme value is 2/3 because that's the y value where the critical point is. So again, I just figured out where the first derivative was 0 or undefined to get the critical point. I plugged that in to get the extreme value that goes with that critical point. Well, let's try another. This is 1 over x minus the natural log of x. And if I want to find the critical points to this, I have to find the first derivative. Well, before I find the first derivative, let me write this as x to the negative 1 minus the natural log of x. When I take the derivative of x to the negative 1, I get negative x to the negative 2. The derivative of the natural log of x is 1 over x. And to write that more nicely, this is negative 1 over x squared minus 1 over x. And notice that this is undefined. This makes no sense when x is 0. Critical points. I have 1 when x is 0 because the first derivative is undefined if I put 0 in the bottom of that. I also get a couple where this thing equals 0. I also need to figure out where the first derivative is equal to 0. So I get negative 1 over x squared minus 1 over x equals 0. I'm going to multiply by the common denominator, so I'm going to multiply everything by x squared. When I do that, this equation becomes negative 1 minus x equals 0. And so I get x equals negative 1. Those are my critical points. I got the one where it's undefined, and then I got the one where the first derivative equals 0. Notice when I multiply by x squared, it allows me to cancel a lot of this stuff. Negative 1 minus x equals 0. To find the extreme values, I'm going to write EV. Well, notice if I take x equals 0 and plug it in, f of 0 is undefined as well. So there is no extreme value when I plug in 0, because it's undefined there. But I do get an extreme value when I plug in negative 1. I get 1 over negative 1 minus the natural log of negative 1. Well, that's undefined as well because the natural log makes no sense. So there's no extreme value there as well. So these critical points don't give us extreme values when we solve. These critical points turn out to give us two places that are undefined when I plug it back in. So since these critical points are outside the domain, then none of them are valid for extreme values. So these are two critical points, but no extreme values going with them, because I didn't get anything out that made sense when I plugged them in. Here are some absolute max and minimum problems. The reason I can find an absolute max and min is because I have a closed interval. Whenever the interval is closed, I can find absolute max and mins. To find absolute max and mins, I find all the critical points and the max and mins that go with them. And I also have to check the endpoints as well, because the endpoints could also be the biggest or smallest value. If you'll notice at the example we did before, this graph here had a minimum value at the critical point. That turned out to be the critical point, the valley. And it had a maximum value at the end point. So whenever you do these closed interval ones, you get critical points and end points of the interval. And you check them all to see which gives you the biggest and smallest y values. Well, so the endpoints are 4 and 8. And to find the critical points, I have to take the derivative. Figure out where it's undefined or 0. 3x squared minus 4x minus 5. That's my first derivative, and it's defined everywhere. So I only have to worry about where this thing equals 0. Lots of ways to solve it. I'm going to use the quadratic equation. So x is negative b, which is 4. The square root of b squared, which is 16, minus 4 times a times c, all over 2 times a. That's 4 plus or minus. This is 16. And let's see, that's 60 plus 60 over 6, which is 4 plus or minus the square root of 76 over 6. There are two answers there. I'm going to write them as decimals. So I got 4 plus the square root of 76 over 6. That's 2.12. 4 minus the square root of 76 over 6 is negative 0.79. Those are my critical points. 2.12 and negative 0.79. So now if I want to figure out my absolute max and mins, I plug all of these into the function. So I take my critical points, which is 2.12 and negative 0.79, and I plug them in to f of x. When I plug 2.12 into f of x, I get 2.12 cubed minus 2 times 2.12 squared minus 5 times 2.12 plus 6. That y value is negative 4.06. Then I plug in negative 0.79. When I do that, I get 8.21. These are possible extreme values. And then I also have the endpoints, 4 and 8. So I plug those in. First I'll plug in 4. That gives me 18. And I plug in 8. And that gives me 350. So the absolute maxima is the 350. And that happens at x equals 8, which happens to be an endpoint. The absolute minima, which is the smallest one, that's negative 4.06. And that happens at x equals 2.12, which happens to be a local, or which happens to be a critical point. So I had one of the absolute maximas occur at the endpoint, and I had an absolute minima occur at a critical point. So they can occur at any of them. You just have to find them all and check them. The endpoints and the critical points all get plugged in. The biggest y value is the absolute max. The smallest y value is the absolute min. Oh, let's do it again. Here's another one. The reason this one will be tricky is because we need to take the derivative. Remember, cosine squared of x is the cosine of x all squared. So when I take the derivative, I have to use the chain rule. I get 2 times cosine of x to the first. The derivative inside the box, the derivative of cosine, is negative sine. So I get negative 2 cosine x sine x. Notice sine and cosine are defined everywhere. So to find critical points, I just have to set this equal to 0. And what I get is where the cosine of x equals 0, or where the sine of x equals 0. Remember, we're from 0 to pi. Well, the cosine of x equals 0 at 0 radians and pi radians. The sine of x equals 0 at pi over 2 radians. So these are my critical points. Remember, I also have to have my endpoints, which are 0 and pi. So it just works out that my critical points happen to be at endpoints as well. So to find my extreme value, I take my critical points, 0, pi, and pi over 2, and I plug them into my original function, which is cosine squared of x. Cosine squared of 0 is 1 squared, which is 1. Cosine squared of pi is 0 squared, which is 0. And cosine squared of pi, the cosine of pi is negative 1. So the cosine squared of pi is negative 1 squared, which is 1 as well. Cosine squared of pi over 2, the cosine of pi over 2 is 0. When I square it, I get 0. So you can see that I have absolute maxima that happen at 2 places. The absolute maxima is 1, and it happens at 0 and pi. The absolute minima is 0, and that happens at pi over 2. And you can tell that just by looking at the y values. That's what you can do on a closed interval. On a closed interval, just look at the y values. The biggest are the maxima, and the smallest are the minima. Here's another example. I automatically get the endpoints to check, which is 2 and 6. I also have to find the critical points. To find the critical points, I'm going to take the derivative. I get 1/2 times x minus 2 to the negative 1/2. That's inside the box, or outside the box. Inside the box is 1. So I'm going to write this so it's easier to solve. The 1/2 is the square root. Since it's negative, it's on the bottom. Well, there's my first derivative, and notice it's undefined when x equals 2. If I put 2 in there, I get a 0 on the bottom. So I get a critical point at x equals 2 where it's undefined. I also get a critical point where it's equal to 0. So to figure out where this is equal to 0, I set it equal to 0. Multiply both sides by the denominator. Probably so you can see it would be nice. Multiply both sides by 2 root x minus 2. Here they cancel, and I end up with 1 equals 0. Because on this side I get a 1 left. 0 times anything is 0, which doesn't help. So there's really just 3 places. And notice one of the critical point is an endpoint in this case. So to find the extreme value, I take my critical points, which are 2 and 6, and I plug them into my function, which is the square root of x minus 2. That's what the 1/2 power is. And so this is the square root of 2 minus 2, which is 0. This is the square root of 6 minus 2, which is 2. So there's an absolute maxima, and that's 2, and it happens at x equals 6. There's an absolute minima, and that's 0, and it happens at x equals 2. So you find your critical points and your endpoints, and you plug them in. The biggest y value is the maxima. The smallest is the minima. Just like the problems above. One more problem. Here's a story problem. This is actually one we've done before, except we thought about it a different way. This is that same problem where you throw a stone into the air and you get a function that tells you how high it is above the ground. And you want to know when it reaches its max height and figure out what that maximum height is. And notice they're giving us a closed interval. So this is just like the problems we did before. We want to find the maximum and minimums, and we get the endpoints for free. T equals 0 and t equals 6. Those we automatically get to count. We also get to count the critical points. To find the critical points, I take the derivative, and I get negative 32t plus 64. That's defined everywhere, so I'm just going to take that and set it equal to 0 to figure out where the maximum value is. Here's the funny part. Remember, the derivative of position is velocity. And the way we did this problem before was we said, oh, well, the velocity is going to be 0 at the highest point because it turns around from moving up to moving down. Here's another way you can think about it. This motion is a parabola, and at its highest point, you're going to have a critical point. So another way to figure out when the stone reaches its highest point is to set the first derivative, the slope of this thing, equal to 0. Notice that's the same thing we did before, setting the velocity equal to 0. And so we get 64 equals 32t, and 2 equals t. So we know that we have another critical point at t equals 2. So now we want to find the extreme value. Remember, we just want the maximum in this problem. So the extreme value, I plug these into the height. So I got t, oh whoops. Let me set this up correctly. So I have t equals 0, t equals 2, and t equals 6. And I want to look at the extreme values by plugging these into the function. The function in this case is negative 16t squared plus 64t plus 192. So I have t equals 0, t equals 2, and t equals 6. Notice when I plug 0 in here, I get 192 out. Now I'm going to plug 2 in there. You got negative 16 times 2 squared plus 64 times 2 plus 192. That gives me 256 out. And then I plug a 6 in there to see what that does for me. And that gives me 0. So I know there's an absolute max. And since this gives me the height, it's the max height of 256. In this case it's going to be feet, but that's just because I know the units of acceleration in the problem. And there'll be an absolute min of 0, but that's when the rock hits the ground. So the absolute max height is 256 feet, and it happens at t equals 2. In this case, it would be seconds. I know the units only because I know how the acceleration is being measured. But the absolute max height is 256. It happens at 2 seconds. The same problem we did before, except now instead of thinking about it as velocity turning around, we can just think about it as finding the critical point, where the first derivative is 0. 256 feet for the maximum height.